Yes, we are live on our YouTube channel. It's 7 o'clock. Good evening. Namaskar to everyone. This is Dr. Govind Lakhotia, physics professor and a visiting faculty here at Professor Rajendra Singh Science Exploratory, Nagpur. It gives me a great joy as a teacher of physics and a member of Professor Rajendra Singh Science Exploratory, Nagpur, to welcome you all to this special celebration of learning, that is making maths make sense, yes, but why fame, with Dr. E.D. Southall. This is not just an academic gathering. Today, we celebrate the spirit of inquiry and the power of education on a very meaningful day for all of us, that is Teachers' Day. In India, we celebrate Teachers' Day on 5th of September every year, the birth anniversary of Dr. Sarvapalli Radhakrishnan, our former President of India during 1962 to 1967. He was an extraordinary philosopher, teacher, and statesman who reminded us that a society is built on the minds of the teachers. He believed that teachers are not just transmitters of knowledge, but a torch bearers who ignite curiosity and critical thinking in young minds. This year, our Teachers' Day coincides with the auspicious days of Lord Ganesha Festival. In our homes, streets, and institutes, Lord Ganesha reminds us that the true learning begins with humility and inquiry. He is a Vignaharta, that is the remover of obstacles, also the god of wisdom and intellect. How symbolic that we celebrate knowledge, curiosity, and teaching these very days. Just as Ganeshotsav brings communities together in devotion and joy, may today's session bind us together in the spirit of learning. Dear viewers, we have a very special guest today, Dr. E.D. Southall, who have joined us from UK for this session. To set the tone for this session, I invite our 8th grade student, Master Mihir Deshpande of Professor Rajendra Singh Science Exploratory to present a welcome song. Mihir.
Thank you, sir. So I will start now.
Can we share, can we unshare the screen, Dr. Southall? Yes, thank you.
Should I
Yes,
start, sir?
yes, Mihir.
Yes. स्वागतं शुभ स्वागतम् अथ स्वागतं शुभ स्वागतम् आनन्दमङ्गलमङ्गलम् आनन्दमङ्गलमङ्गलं नितप्रियं भारत भारतं नितप्रियं भारत भारतम् स्वागतं शुभ स्वागतम् अथ स्वागतं शुभ स्वागतम् नित्यनिरन्तरता नवता नित्यनिरन्तरता नवता मानवता समता ममता सारथि साथ मनोरथ का सारथि साथ मनोरथ का जो निवार नहीं थमता संकल्प विजिताभिमतं संकल्प अविजिताभिमतं नितप्रियं भारत भारतं नितप्रियं भारत भारतम् स्वागतं शुभ स्वागतम् अथ स्वागतं शुभ स्वागतम् अथ स्वागतं शुभ स्वागतम्. Thank you.
Well, thank you, Mihir, for this melodious beginning. May I now invite Dr. Seema Ubare, Director of Professor Rajendra Singh Science Exploratory, to deliver the welcome address.
Thank you, Govind. This is Dr. Seema Ubal and Namaste and Suswagatam. Welcome and good evening to this today's program. On behalf of Professor Rajendra Singh Science Exploratory, I welcome Dr. E.D. Southall sir and the other dignitaries present over here Zoom platform. Today we are celebrating National Teachers Day. And on this program is being organized by Professor Rajendra Singh Science Exploratory. I would like to tell you something about Professor Rajendra Singh and our exploratory. Professor Rajendra Singh Allies, who was also fondly known as Raju Bhaiya, was a teacher par excellence. He served as a professor of physics at Allahabad Vishwavidyalaya and later on gave up the job to become a full-time social worker. He was a teacher par excellence. And to commemorate, the exploratory is being named after Professor Rajendra Singh alias Raju Bhaiya. At this exploratory, our tagline is explore, experiment, and excel. That is the children from 6th standard to 9th standard. This is an after school program, and these children from 6th to 9th standard, they join us for this yearly program. It is a after school program. That means they come to the exploratory every week for 2 hours and perform activities related to their science curriculum from their school. By doing so, the children try to do the activity by themselves. They read out the material given to them. They try to work on it and finally take the data for themselves and try to arrive at some result. So this gives a lot of confidence in them, and that is also relating the theory with the practical. So this is how the exploratory is working. Presently, we have got around 250 students who are enrolled in the after school laboratory training program. And there are few more programs in which the children they visit once in a month or they come for a visit and have an experience of hands-on experiments, because the activity generally these school students do not get an opportunity to work on these scientific activities by themselves or in a single manner. So here they are provided with experiments and the apparatus which they can perform and get the data for themselves. And by doing so, they study various aspects, and that is how they try to explore, try to experiment, and finally try to excel. This is just inculcating the scientific temperament amongst them, considering the scientific aspects behind all the things happening around us. And that is how we are working continuously. This is our third year. Earlier, the exploratory was established in the year 2015 and it recommenced in the year 2023. And accordingly, now we have entered into third year, and I am very happy to share with you that there are around 250 children right now registered with the exploratory, and there are 100 or even more children who are visiting on monthly basis or once in a while they are visiting. So that is what I wanted to share with you about our exploratory. And on behalf of exploratory, I extend a welcome to you, and I um expect that whenever you will come to India, do visit Nagpur and our exploratory as well. So once again, welcome Dr. E.D. Suthal sir, other dignitaries, and my dear students. And over to you, Govind, now. Thank you very much.
Well, thank you. Thank you so much, ma'am, for setting a thoughtful tone for today's session. Now, friends, comes a truly exciting part of the evening. We are extremely fortunate to have with us an international mathematician who has dedicated his life in making learning joyful and meaningful, Dr. E.D. Suthal, who is maths lead at Oak National Academy, United Kingdom. I request Mr. Nikhil Jaipurkar, visiting faculty here at Professor Rajendra Singh Science Exploratory, to introduce Dr. Southall to the gathering. Over to Nikhil.
Thank you, sir. Am I audible?
Yes, yes.
Okay. So it is my privilege to introduce Dr. E.D. Southall, a distinguished mathematics educator, author, and a subject leader. He currently serves as the math subject lead for Oak National Academy and as a mathematics specialist for the secondary PGCE at the University of Huddersfield. In these roles, he has overseen the design and development of nearly 2,000 open license, fully resourced mathematics lessons, making high quality learning accessible to the countless children. Dr. Southall is also a highly regarded author of six influential books on mathematics, including the best selling Pedagogy and a Subject Knowledge Guide titled Yes, But Why? Teaching Us for Understanding in Mathematics. He has also the recently published book titled As a Bothered About Maths. Beyond his academic contribution, he plays an active role in wider mathematical community as a senior member of the Mathematical Association and as a trustee of Exo Maths, where his work continue to shape both mathematics teaching and curriculum development. Please join me in a warmly welcoming Dr. E.D. Southall, whose dedication to mathematics education has inspired teachers, students, and fellow educators alike. I now invite him to kindly deliver his speech.
That's an incredibly kind welcome. Thank you, everybody. I'm very honored for the invitation to speak to you today. And as has been previously mentioned, I have a doctorate in maths education, and I'm going to talk to you a little bit today about something that I feel very passionate about, which is trying to communicate to children sense making around mathematics, because mathematics can be quite a complicated and abstract subject, and often we can miss opportunities to make it feel easier to understand with powerful images and representations. So I will be sharing with you a few examples of this work, and hopefully you will find them interesting. And along the way, we shall do a little bit of maths together as well. So you will have to think as well as listen. I always like to start with a puzzle. So on your screens now, you should hopefully see a square, and that square is broken up into 4 different triangles. And you can just do this in your heads, or you can do some drawing if you like. But I ask you, what fraction of this square do you think is shaded pink?
2 by
And
4.
I will. You can use the chat to type to put your answers in, but please give yourself some time to think. Okay, so in the chat, I'm going to count down from 5, and I would like you to write your answer if you haven't already. Do not worry if this is right or wrong, but we'll see what people have written. So 5, 4, 3, 2, 1. Excellent. Lots of responses. Thank you. Now, what I love about this puzzle is that it's easy to access, and you can feel success from guessing the response. But also there is a bigger challenge in proving what you think the answer is. So you can guess roughly that this shape is shaded half pink, or two out of 4 equal parts pink. But proving that this is true is more difficult. For example, if we change to percentages, how can we be sure that this is exactly 50% and not 51% or 49% or anything like this? And this is a more challenging task, But what I love about this puzzle is that you can show a moment of enlightenment just with some simple extra lines. So I'm going to show you how I would do this puzzle. So here I have simply added two straight lines, and suddenly we can now see visually that we have four rectangles instead of one square, but it's still the same shape. And in each of these four rectangles, you can see that the diagonal divides it into an equal pink triangle and white triangle. And therefore, if half of each rectangle is pink, then half of everything is pink. And therefore, we have proved that exactly half of this shape is shaded pink. And I love this puzzle because it's easy to access. It has additional challenge to prove, but it has a nice, simple, and understandable solution that convinces people very easily that it must be exactly one half. And in fact, if you think about it more, I did not tell you where this point is. And so this point could be anywhere. We would call it an arbitrary point. So this point here could be over here, it could be over here. The result will always be the same. And in fact, if you placed it right in the center, then again, you have quite an easy visual solution to this problem. So that's a nice explanation of something that is important to me, being able to make sense of something in maths rather than just getting the answer correct. And for me, this is very important with learning maths because without being able to make sense of maths, then you can imagine all the different bits of knowledge that you need to hold in your head for maths, and they have very weak connections between them. In the UK, if you learn the whole of the maths curriculum for school, there are over 300 facts to learn, which is a big task. But in fact, if you can learn the concepts underneath all of these topics, there is not many things to master. And so what we are trying to do is move away from this model of understanding things as separate facts and move towards a more interconnected understanding where we can see patterns across topics and we can see how things relate to each other across all of the maths that we need to learn. Here are some examples of the sorts of things that I was told when I was a student that do not contribute to making sense of maths, but instead are provided as magic rules that someone knowledgeable tells me and I am expected to apply. And so sometimes these will get me the answers that I need, but I will have very little, if any, understanding of why I am doing those things. So I was told to add a zero when I am multiplying by 10. I was told to borrow the one or borrow the three or something like this when I'm doing a subtraction. And this idea of borrowing is very ambiguous and can be easily misunderstood. And how do I know as a child what I can borrow from and how and why are we using this word borrow? It's a strange word to use in maths. And when solving an equation, I was told switch the side, switch the sign, which is where if you had a plus, my teacher would tell me to literally move it with my imagination across the equals sign and it becomes a minus. And all of these things are not really true. They are intended as a way of making the maths feel easy, but really what they do is make it feel more mysterious and harder to understand why anything is working. It just becomes like magic tricks and strange ideas that your teacher is telling you. I want to give you an example. So this is a number trick for multiplying by 11. Okay. And so we have an example here, 11 times 36, 11 multiplied by 36. And the trick is that if I take the 3 and the 6 and I pull them out as individual digits, 3 and 6, and I add them together, I get 9. And if I place this 9 between the 3 and the 6, then I get 396. And the answer to 11 times 36 is 396. It's 396. And this is true. So I have the correct answer, but the method is very, very strange. The method it feels like a trick. I take the second number, I turn it into two individual numbers, 3 and 6 instead of 30 and 6. I add them, I place it inside the number to create 396. And you may not believe this is true, but if you work it out, you will find that this is true. And I can do this for many numbers. Okay, so you can try this with a different digit. If you do 11 times 23, okay, you'll take the 2 and the 3, add them together and get the 5, and then place it between the 2 and the 3, and you'll get 253. Okay, and it works, but there's no sense making attached to this method at all. We are just doing it because someone has told us to do it. And then when I show you that it's right, it feels exciting, but you have no understanding of what's going on. This is not a great way to learn maths. This is a nice trick, but it's not good for understanding what is happening mathematically. Here's one more example. 11 times 24, 2 plus 4 is 6. Put it inside the 24, 264. This is my answer. Okay, now one of the problems with these types of tricks is that they are inflexible. And so they will only work for a small amount of cases. And then when it breaks, we have no idea what to do because we didn't understand it in the first place. So here's an example. If I do 11 times 39, so now I add the 3 and the 9, and I get 12. Well, what do I do with 12? No one has told me what to do with 12. So now it's inflexible and I'm confused again and I don't like this method. I could put the 12 in the middle and I would get 3, 1, 2, 9. But you will probably be thinking this is much too big to be the answer. But I'm doing what I was told. I've added the two numbers, I've stuck them in the middle, I get 3, 1, 2, 9. It doesn't make sense. Or similarly, I could say, okay, I get 12, so therefore I add 1 to the next column over, the hundreds, and I put the 2 in the middle, so I get 429. And in fact, this is correct. But now I've had to learn a new case. So I have two different cases in my head now for when I times by 11. And neither of them make any sense. And what happens when I get bigger numbers? And what happens when I don't times by 11? And suddenly this whole idea comes crashing down and it's not very useful. This is an example of teaching a procedure or an algorithm without having any sense making attached to it. Now, because you are all very smart, I'm going to spend just a second explaining why this idea, why this trick actually works mathematically. Okay, so we'll take this example. This is the trick. We add the 2 and the 4, we get the 6, we put it in and so on. But let's now consider what's really happening as a proper mathematician. Okay, 11 times 24 is what we are starting with. What I'm going to do here is break this down like this. Okay, So I still have the 11 here. The 24 I have decomposed into 10 times 2, this is 20. And 4, this is my ones, 4 ones. Okay, now the reason I'm doing this is to prove to you why this method works over here. Okay, hopefully you can follow this line. The next line, let's spend a moment. We have 11 times 10 is 110, times 2 is still here. So this part here is just here. And then we have the 11 times 4 at the back. Okay, it's slowly turning into this over here. And then one more step. I've now got 100 times 2. So I need another 10 times 2. Here's the 10 times 2. And then I have 11 times 4, which I'm breaking down to 10 fours and 1 4. 10 fours on 1 4 is 11 fours. Okay, but what you can see here, now I've broken this down. I've broken it down into hundreds and tens and ones. And here's the hundreds, and here's the tens, and here's the ones. And this 2 plus 4 here is this 2 plus 4 here. Now, I don't expect you to follow this straight away with just me saying it in 1 minute. But if you can follow what's happening on the right-hand side, this makes sense. If you follow the left-hand side, this is a trick with no understanding attached. So if you are ever told these sorts of tricks, it's a really useful mathematical task to try and take it to pieces and understand it mathematically, to have that deep understanding of what is happening. Okay, let's move on. Here's another algorithm that we use frequently, but we don't necessarily understand. We're doing it because we're told to do it. So on the left-hand side here is our standard addition algorithm, our column addition. And we typically say, okay, we take the ones or the units and we say 8 plus 5 is 13. And then remember this vocabulary from earlier. You might hear that we carry the 1 or something like this. But what we're doing is putting the 1 in the tens column here because it's 10 ones, which is 110. And then we're adding the 5 and the 3, but these are tens, so 50 and 30, plus the 10 down here, and so on. I know you are familiar with this algorithm. However, the challenge for you is, why do I have to move this over here? What happens? What happens if I don't? Okay, so on the right-hand side, this is when I don't. So I say 8 plus 5 is 13. I'm just going to leave the 13. 5 plus 3 is 8, or 50 plus 30, if you like, is 80. And 200 plus nothing is 200. In our heads, we might think 2 plus 2 plus 0 is 2. But we should really be thinking this is 100. So this is 200s, not a 2 on its own, because that can lead to more confusion. Anyway, is this wrong? By leaving it as it is it wrong? Well, it's not wrong. The problem that we have now is that it does not read as a decimal number anymore. Okay, if I read this as a decimal number from left to right, it would be 2813, which is a decimal number, is 2,813, but this is incorrect. This is not a decimal number. What we have now is 3 groups of quantities. We have 200s, we have 8 tens, and we have 13 ones. Now, if I add all of that together, I will get as a decimal number 293. Now, the reason I'm telling you this is because these two ideas show you why we do this carrying here, this exchange of 10 ones into 110. The reason we do it is so that our answer is preserved as a decimal number. Okay, so that our answer, we can read it as a decimal and say 293. If we don't do that exchanging, then we do not get a decimal number. We get three groups of quantities. It does not read as the right number. Let's try this with subtraction. So here is our standard, a standard column subtraction. And typically what you might want to do is say, okay, 3 subtract 6, 4, I can't do this, so I'm going to exchange. So I want you to try this and see what you come up with. Why does this break? How have I broke the algorithm? Well, if you work it through, you come up with this. And the reason it feels wrong is because, again, this is not a decimal number. And the reason this has happened is because the number on the bottom, the subtrahend, is greater than the thing we began with. And when you use this algorithm normally, the top number is the big number, the greater number. If you don't do that, this happens and you get this strange value at the end. Now, this is the same problem as before. This answer is actually correct, but it's not reading as a decimal anymore. So we have positive 7 ones, we have a positive 8 tens, we have 0 hundreds, but we have a negative 1,000. Now, if you add together a negative 1,000 and a positive 87, you will get the right answer as decimal format. And this is the problem with this algorithm. We do it without thinking about what it's doing. But actually, if we understand it fully, we can interpret what's happening in any circumstance. Okay, let's move on to some visual representations. Now, here is a simple multiplication, 54 times 16. Now, this is a good example of seeing as a student, you instantly want to find the answer without really realizing what it's telling you and how it works. And I want to show you a link between this and what I call the grid method. So we're going to use something called an area model and link this to geometry. So 54 times 16 was the question. I'm turning this now into a rectangle. And one dimension is 54 and the other dimension is 16. So the length is 54 and the height is 16. Okay, so therefore the area of this rectangle, to calculate it, I'm still going to do this multiplication, 54 times 16. This is just a different representation of the same thing. But what this model allows me to do is show how partitioning really supports how to make this question easier. So I'm going to split the 54 like this. So the 54 is now a 50 and a 4. Okay, but look between the two. The rectangle is not changing size. The large rectangle is not changing size. So the answer is staying the same. What's happening is I'm partitioning it into two smaller rectangles. One of them is 50 times 16, this one, And one of them is 4 times 16, this one here. Okay, now I'm going to do the same on the left-hand side. I've partitioned again, and my 16 has become a 10 and a 6. It's still 16 overall, and still overall my whole answer, the large rectangle, the area, is not changing. However, I'm making it into 4 smaller pieces now. This piece is 10 times 50. This piece is 10 times 4. This piece is 6 times 50. And this piece is 6 times 4. And those are 4 different areas, but added together, they are all still the same as 54 times 16. Now, why would I do this? Well, 2 reasons. The first reason is these are much easier multiplications for me to do. There's more of them, but all of them are much easier. They are smaller numbers or they are round numbers like 50 and 10. You can partition this differently if you wanted to. We could have 49 and 5 if we wanted at the top. It's still adding to 54. But the reason I don't want to do that is because that makes it harder, not easier. 49 times something is horrible. 50 times something is very nice because it's a round tens number. This is the same as this method. This is the grid method. If you've done this method before, your teachers may have shown you this as a way of making multiplication easier. Where it comes from is this kind of imagery, this idea of finding the area of a rectangle. Now, this concept works for division as well. Let's try this. 336 divided by 16. Okay. This is how you may traditionally do it with our, we call this in the UK the bus stop method because this looks a little bit like a bus stop. But we're doing the area model this time. So in fact, if you think before we had 2 dimensions and we had to work out the area, well, in this example, because it's division, I am working with the inverse operation. So I have the area. The area is 336, and I only have 1 dimension, which is 16. So with division now, I'm trying to find out the length. And I'm going to make it nice and big so we can all see it. Now, the method for solving this way is again related to partitioning. So I am going to partition this rectangle. And the first partition I want to make is this. And the reason I have chosen this is because 160 is easy for me because I know what this length will be. Something times 16 is 160. Well, I know this is easy for me, so this must be 10. This is why I have chosen 160 here. You don't have to choose 160, but it's a nice, easy one to go to. So now I have part of my answer. I have part of my length of my rectangle. I'm still left with this piece. So I'm going to break this up again. And I'm going to break it up into another 160 because I know this is 10. And now I'm left with a nice easy 16, which is a 1 here. Okay, so again, I've partitioned my area into 3 smaller areas to make all the maths easier for me. And I have a length of 10, a length of 10, and a length of 1. So the total length here is 21. Therefore, my answer is 21. Okay, now you may be thinking, he has picked easy numbers. This is cheating. Well, I picked easy numbers to show you the model. Let's make this slightly more difficult. Now we have 337 instead of 336. So this is not an easier number because it will not go exactly. Let's do it again. Well, we have 160, 160, and 16. We are left with a 1. This doesn't divide exactly, so I'm going to leave this as a fraction and just say 1 divided by 16 is 1/16. So my full answer this time is 21 and 1/16. So this area model is very versatile. It's very good for showing understanding of how multiplication works and how we can play with those numbers and partition those numbers to make the question easier. It works with division and it works with multiplication. This in the UK is basically something we call chunking, where you take chunks off the number until you have a nice easy answer. So this was chunk 1, 2, 3, 4 in this example. Okay, let's move on. I'm going to show you a demonstration now. So here's fractions. Fractions always scare me, so someone might need to help me here. A third plus a quarter. Okay, now your head probably goes straight to thinking that because the denominators are different, therefore I must change them so that they are the same. And this is the algorithm in your head talking. And that's fine, but it doesn't make it make sense. It's just telling you what to do to get the answer. So let's make this make sense. Why do we need to change these denominators? Well, with a nice visual model, we can start to understand why it is that we need to change these fractions. So here we have one whole. These are called fraction strips. And we have it represented as 3/3. And we had 2/3 as the question, plus a quarter. Okay, here's a whole separated into quarters. And if I add a third and a quarter like this, which is what the question was asking me to do, you can see visually that this line, which is where my answer is on a number line, so imagine this is 0 and this is 1. This is my answer, 1/3 plus a quarter, but it does not line up with quarters, and it does not line up with thirds. If I was to use quarters, then my answer is 2 and a bit quarters. This is not very accurate. If I was to use thirds, then my answer is 1 and a bit thirds. This is also not very accurate. But using these fraction strips helps you see why it's not okay to use quarters and why it's not okay to use thirds. We need a new tool. We need a new method to be able to tell ourselves what the value of this is here. This is essentially our problem. How big is this? Okay, if I give you the numbers on the number line, you start to get a good idea and we can estimate the answer. So it's going to be 0.5 something and just less than 0.6. But it doesn't add up to thirds and it doesn't add up in quarters. But it does add up in twelfths. So if I look at twelfths, I can see 1, 2, 3, 4, 5, 6, 7 twelfths fits exactly on this line here. Okay, so we've understood that there is a need to change the fractions. And using this visual model, you can see that twelfths lines up perfectly. And from here, we can start to understand why we must change from thirds to twelfths and from fourths to twelfths. So thirds is 4/12, a quarter is 3/12. So overall, we have 7/12. What about multiplying fractions? Well, I find this difficult because I find the word times or multiply needlessly confusing in this example. So a quarter times a third. What does this mean? Like, what am I doing? What situation would I need to do this operation in? Otherwise, this is very, very abstract. It's just, I see a fraction, I see another fraction, I times the tops, I times the bottoms. This is the algorithm, but it doesn't necessarily make any sense. Like, why are you doing that? Well, let's have a look at an example. I'm gonna come out of this and go into a tool. So we had, what was my example? A quarter times a third. Okay. And what I'm going to do is I'm going to take a rectangle and I'm going to build a rectangle that is 4 by 3. I'll zoom in here. Okay, a quarter times a third are the two things I'm trying to work with. And a quarter is represented as columns, and a third is represented as rows. Okay, so if I was to color this in, that set of squares here, this is a third, all of these. And this set of squares here is a quarter, okay, because there are 4 of them. Okay, so I'm going to shade these in. I'm going to shade in my third. This is my third. That's my third shaded. I'm going to change my color. We'll do blue. And now I'm going to shade in a quarter. Like this. So in this diagram now, I have a third shaded and a quarter shaded. Now, what this is actually doing, it's saying what is a quarter of a third, or what is a third of a quarter. And the reason it can be either of those things is because multiplication is commutative. I can do it in either order. If you want a simpler example, 2 times 3 is exactly the same as 3 times 2. The order doesn't matter with multiplication. So I'm either saying a quarter of a third or a third of a quarter. That's what the maths is trying to do. And this diagram shows me exactly that. Here's my third, here's my quarter, and if I want to highlight it, I'll use this color. This square here is a quarter of a third or a third of a quarter. If you look at it from this direction, then it is a quarter, because it's one of 4 pieces, of a third of the shape. And if you look at it from this direction, it is a third, there are 3 equal pieces here, of a quarter of the shape. So this is my answer. My answer to a quarter times a third is this thing, this square here. But what number is this? How can I interpret this? Well, let's count these up. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 squares make up my whole. So 12ths is what I'm dealing with. Oh, my cursor's not working. And I have only one of them represented. So this is my answer, 1/12. And if we go back and we times the tops, we get 1. And if we times the bottoms, we get 12. Okay, so the maths that is being done is times the tops times the bottoms. The sense making is that what this is doing is finding a quarter of a third or a third of a quarter, which I can show visually in a diagram like this. I think we have time just to do one more example to show you how versatile this is. So let's move along here. And this time we'll do 2/3 times 1/5. Okay. So I'm going to draw a rectangle and I want thirds and fifths. So I'm going to have 1, 2, 3, 4, 5 here and 3 down like this. You could do 3 and 5 or 5 and 3. It doesn't matter which way around your rectangle is. Okay. And the reason I've chosen 5 across and 3 down is so that I can separate this into thirds really easily, and I can separate it into fifths really easily. So, let me get my color. Let's go pink. 2/3 are going to be these rows here. This is a third, this is a third, and this is a third. So 2/3 is this represented. Almost there. So 2/3 of my shape is shaded. Think of this as the squares that you can see here. And then I also want to shade a fifth. So I will shade a fifth down. 1/5. Okay. All of these columns are fifths. 1, 2, 3, 4, 5. Okay, so all that is left is I need to interpret my answer. And my answer is these 2 squares this time. This is what is shaded both ways. So there are 2 squares shaded out of 15 squares. This is my answer. 2/3 multiplied by a fifth. Mathematically, the algorithm, I can just say 2 times 1 is 2, 3 times 5 is 15. The answer is 2/15. Brilliant. But if we want to understand what the maths is doing, we are saying 2/3 of a fifth or 1/5 of 2/3. And if we look at it in this direction, this is 2/3 of 1/5. And if we look at it in this direction, it is 1/5, 3, 4, 5 of 2/3. Now you might be thinking, I don't want to draw this every time I have to multiply fractions. It will take forever. And you're right. This is not an efficient way of solving the problem every time. The efficient way of finding the answer is multiply the tops, multiply the bottoms. But the way to make sense of the maths is through a visual representation, similar to this. All right. Next, I want to show you averages. So we're just going to do 2 more. So averages, there are 3 averages that we deal with mostly in statistics. We have the mean, the median, and the mode. And the mean is a great example of just do as the teacher tells you and hope for the best with the number that comes out. And often we are told, add them up and divide by however many there are. So for example, if I had a data set that was 3, 4, 6, then I would say add them up, 6 plus 4 plus 3, divide by however many there are. I'm going to divide this by 3 because there are 3 numbers. And this gives me the mean. But that doesn't tell me what the mean is, and it doesn't tell me what the mean is for, and it doesn't tell me why the mean is useful. It's just do an algorithm, give me the number that comes back. So we're going to try this instead with a different visual model, which is over here. Okay. So this is a visual representation of 4 different numbers. Okay, we have 2. We have 3. Oh, let's try this a bit more slowly. We have 5. And I think this is 10. It's not typing in, so I'm just going to delete those. But you can count how many squares we've got. 1, 2, 1, 2, 3, 1, 2, 3, 4, 5. Double that, 10. So my data set is 2, 3, 5, and 10. And the algorithm says, add all of that up and divide by however many there are. So I would say 2 plus 3 plus 5 plus 10 and divide it by 4 because there are 4 different numbers. But it doesn't really explain anything in a sense-making way. So I'm going to tell you what this thing is actually doing. What we're trying to find is the center, the number that represents the middle of this data. And by representing it in this way, what I can actually do is just level it all out like this. Okay? This is the mean. The mean is this line here. Leveling everything out, finding the center, finding what best represents this data, the central tendency. It is this 1, 2, 3, 4, 5. Okay? If you do it through the algorithm, you will do 10 plus 5 is 15, plus 3, plus 2, and then divide it by 4, and you will still get 5. But what that number is telling you is where this sits centrally. Can you make them all even? Can you make them all the same? And understanding it in this way helps you solve problems much, much easier. So here's a problem. It says the mean of 4 numbers is 6. What is the 4th number? The mean of 4 numbers is 6. What is the 4th number? Well, we know that we know the first 3 numbers because they're represented here. We have 4, 6, and 6. Okay? So if I've got 4, 6, and 6, and the question is saying, what's the 4th number if the mean of everything is 6? Well, using this representation, I can just make this very easy. So if the 4th number needs to make everything even as 6, then what I'm going to end up with is 6 on every single row, like this. But there's a 4th number. So let's put that one in. Just going a bit slow, so bear with me. So this is the mean is 6. But remember, I've moved 2 over there, so these belong on this one. So that 4th number must be 1, 2, 3, 4, 5, 6, 7, 8. So the mean of 4 numbers is 6. What is the 4th number? It must be 8, because with 8, I can find the mean like this. And that mean is 6. Again, a powerful visual that supports the understanding of the abstract maths that we are trying to do. Okay, I'm going to finish with just a little thing that I find interesting. We've talked a lot about the maths, but actually there is a side to all of this understanding that is just about language, because maths has some very strange words in it that often don't feel like they make sense, which only makes the maths harder to grasp. So I'm going to give you one example. Shapes. So shapes is have strange names. So we have a triangle, then we have a quadrilateral, then we have a pentagon, a hexagon, a heptagon, octagon, nonagon, decagon, and so on. And what I find strange is that when you get to 5 sides, everything has structure. They all end in agon, hexagon, pentagon, decagon. And agon means angles. So pentagon means 5, pent is 5, and agon means angles, or gon means angles. So if you hear the word decagon, it means 10 angles. If you hear the word nonagon, it means 9 angles. And this structure is universal, and it comes up in some other words as well. So you may have heard the word diagonal in maths. Well, that agon is there, and di means 2. So this means across 2 angles. And orthogonal means an upright angle. All these words are connected. Now this is the cheat sheet for every single shape name ever. And it comes from Greek. So we have a triangle, but really you could call it a trigon. We have a quadrilateral, but you could call it a tetragon. Then they become familiar: pentagon, hexagon, heptagon, octagon, nonagon, decagon, and so on. When you get past 10, we have deca in the word. Triskadeca, tetradeca, pentadeca, gone, hexadeca, gone, heptadeca, gone, and so on. And with the sheet, you can see that the structures continue all the way through to the hundreds. So if I wanted a 25-sided shape, it would be an icosy pentagon. 40 is tetra. Tetra, conta, chi, pentagon is a 45-sided shape. And what this allowed me to do was create ridiculously large shapes and give them their official name. So this, this shape name is this: an octa, hecta, ennia, conta, chi, hexagon. Okay, octa is 8, hecta is 100, so this has over 800 sides. Ennia is 9, so this is 90, and hexagon is 6. So this is an 896-sided shape. So if you are ever asked, or you can tell your parents tonight, I know what an 896-sided shape is called. It's called an octa, hecta, ennia, conta, chi, hexagon. Okay, but the point is, these words are not strange. They're not made up. They have structures. They have reasoning behind them, but often we're not told what that reasoning is. Okay, I've talked for a long time, so I'm going to stop here. I hope you have found some of the things that I've talked about to you today useful. This is me if you would like to get in touch, and these are some of the books that I have written. Once again, I would really like to thank you for your attention and for your invitation today to speak about making maths make sense. Thank you so much, Dr. Govinda. I shall pass back to you now.
Well, thank you, Dr. Southall, for this wonderful session. I am sure many of us will go back to this session again and find some learning spaces with some new ideas bubbling in our minds when it comes to mathematics. Now I invite questions from the curious students in the Zoom room, and even we have few senior educators here in the Zoom room who would like to interact with you. Yes, those who have questions, those who have inquiries can raise their hands, and will allow you to raise your questions directly to Dr. Students, you can raise hands. Or you can
Arya
write.
and Chinmay have raised their hands.
Yes, yes. Chinmay Kulkarni, you can go ahead with your question. You can unmute yourself.
Sir, I didn't understand the meaning of mean. How to calculate mean?
Okay, so the mean is one of three averages that we use. We actually use four, but in schools we usually use three. And they are all measures of the center of data, the middle of a data set. And the reason we need different types is because each one comes with different advantages and disadvantages. So we have the mode, which is the most popular number. Mode is French for fashionable. And this might be useful with something like shoe sizes. So if you wanted to know what the most common shoe size was in a class, you would probably choose the mode. You also have the median, which is the very, very middle value if you put them all in order. And then the one we were talking about was the mean, which is a slightly more complicated method to find a central value by adding up all of the values together and dividing by however many there are. That is the algorithm. And what I was showing you was if you look at that visually, it's as if you are stacking all the numbers and trying to level them all out as a middle point.
Well, so next, Arya, you
Arya,
can ask your
Arya, you can unmute this.
Good evening, sir. I actually
Arya, you are not audible.
doing the
Well, network is weak at your end, I guess. You can turn off your camera and ask your question. Yes.
Good evening. I actually face many queries during division. So, could you please give me some easier tricks for division?
The easiest thing to do with most mental maths is estimating first. So before you start putting a pencil and paper together or anything like that, just ask yourself, what is a sensible answer to this question? What that allows you to do is avoid mistakes or see where you've made mistakes because the answer won't make sense. But also it gives you a good feeling for what we call number sense. So for example, if you were going to divide 60 by 9, then even though that might be a difficult division for you, it should be, if you think about it hard enough, the number itself is going to be close to 6 because 60 divided by 10 is 6. So whatever calculation you do, if you don't come out with a number that's nearly 6, then you know you have gone wrong. And I think this is probably the most useful thing you can do before you attempt any division or multiplication or addition or subtraction. Just take a step back from it and say, what sort of size of number am I expecting to come out of this question?
Well, let's move to the next question. Vedika, you can ask your question.
घरात गेली ती कावे का अर्जंट मध्ये आली आली
Vedika, you can.
आईचा फोन तिला काम आहे जा.
Good evening, sir. Sir, I wanted to ask the trick you told for algorithms addition.
Could you repeat again something about addition?
I said that can you tell me that trick for algorithms of addition.
So the main way of doing addition, well, the most common ways of doing addition are the column method that I demonstrated near the beginning. The reason those methods are used so much is because they are quick, but that doesn't necessarily mean they make sense to us straight away. But by doing them, you can usually do the maths quite quickly, written down. There are some problems with column addition though. Often we will do it by default, so it's our only method that we use. And sometimes simple number bonds can be much more effective. Your knowledge of number bonds and can help you do the maths much quicker. So looking for things like a 7 and a 3, or an 8 and a 2, or a 9 and a 1, and so on. Looking for those easy patterns of numbers to sort of move things around will often make the addition much easier. There is a misconception that people like teachers of maths have some kind of superhuman power with maths. It's not true. Like the big difference with teachers of maths is that we understand how to make the question easier. That's the big thing. Like we know how to play with those numbers to find the easy way to the answer. It's not that we can just hold 12 numbers in our head and have some sort of superhuman power. We don't. We can see the easy way.
Well, Omkar, you can raise your question.
Sir, I was asking for where do you get the books, your books, sir?
Amazon in the UK. I'm not too sure about where you could get them in India,
Yes,
but they are
it's
stocked
available
by.
on Amazon, right? We have your one of yes by with
There you
this.
go. You've got a copy.
Sir, can you get them on Kindle?
Yes, I believe you can. Yeah,
Okay, thank you, sir.
no problem.
Mayuresh, yes.
Sir, my question is that what if we need to find the average of a decimal or fraction number?
It's exactly the same principle. So if you think about the model where I was leveling everything out, you would level everything out as much as you can, and then let's say you had one or two pieces left over, like squares in my example, you would essentially break those down until they were equal. Now, that's just what you would do with a visual model. What that's telling you in your head is you're not going to get a whole number as your answer because they don't go exactly into a stack. So your answer is going to be a decimal because you've got that little bit left over to work with.
Fine. Ridan,
Be same or more difficult?
Yes, sir. Sir, I wanted to ask that do you have any classes or anything?
Not anymore. So my last job, I was training teachers to teach children. Whereas now I work for the government to create online lessons for the whole country.
Okay, sir. So, can I get your email ID so I can ask you questions if I will have?
Yeah, I'll leave that to Dr. Govinda to pass around. That's not a problem.
Okay.
next question will take from Parmi.
Thank you, sir.
Yes, Parmi. You can unmute Parmi. Arav.
Yes, sir. I wanted to ask, you showed that question that 54 multiplied by 16. So can we divide both numbers and then multiply by 4 because we have 4 squares?
Divide both numbers by what?
Sir, they are both even, so we can divide them by 2. Then it would be 27 multiplied by 8. And so we'll have 4 squares. So then we can multiply by 4.
Yeah, you have to be careful with manipulating numbers, but yes, you could do that in theory. The concern I would have is if I start lower, if I divide the numbers before I'm multiplying them, then you have more things to keep track of because you have to basically undo that operation later. But you're absolutely right. What you said there would work.
Okay, sir.
Sarah, next question is from Sarah.
Sir, I have a question that, like today you told a trick about a two-digit number being multiplied by 11. So,
Mhm.
do these type of tricks work for only a certain type of numbers, or do these work
Yes.
for every kind of numbers?
Um, that trick in particular will only work for multiplying by 11. There are a number of different tricks that work for lots of different scenarios. Um, they are typically used to try and improve your mental maths, but they come the reason I was showing it you is that it really highlights the difference between performing something that someone has told you to do and understanding why it works.
Okay, thank you, sir.
Last two questions from students. Sharayu. Shaurya, sorry. Shaurya, you can ask your question. Shaurya Pujari. Atharva.
So my question is that how can we divide fractions?
How can you divide a fraction? Do you mean divide by a fraction?
No, two fractions divide.
It's a good question. So the key thing here is like, what do we mean when we say we're dividing by a fraction? So if you took an example like 3/4 divided by a half, what mathematically you're trying to do is how many halves are there in 3/4? Okay, and that's quite a tricky thing to get your head around because it's very, very abstract. But when you think of it in terms of like how many halves are there in 3/4, as an example, you can at least go back to what I was saying before and say you can start to estimate that answer and say, okay, well, there is 1/2 and a bit in 3/4. And so your answer, is going to be 1 and something. In terms of the algorithm, essentially you're going to flip that second fraction and multiply the tops and multiply the bottoms again. That's the version that doesn't really make sense, but it will get you the answer.
Thank you, sir.
No problem.
Atharva, yes.
Sir, that you told us the trick to multiply a digit by 11. Are there any tricks for other numbers like 12, 13?
Yes. So if you're interested in learning those sort of mental maths tricks, the Vedic maths, I think it's called in general, is the kind of the global term for those sorts of tricks. There are many, many different tricks. Often you can, like, if you look up something like divisibility tests, that's a good starting point. So finding out how a number is divisible by something. For example, you could pick any number and you can find out if it's divisible by 9 by adding up all the digits. And if all the digits added up equal 9 or a multiple of 9, like 18 or 27, then that number will divide exactly by 9. And those sorts of algorithms are a good place to start learning some of those mental maths tricks.
Yes, thank you, sir.
Anaya,
Yes, sir. Thank you. So I had to ask a question which is not related to today's session, sir, but it's
Okay.
a question like I was inquisitive about.
Yes, go ahead.
Okay. So, sir, my question is that why is the value of pi often taken as 3.14, but the calculations of 22 by 7 are like a kind of recurring?
So 22 divided by 7 will give you one of the closest approximations to pi that you can get with a fairly simple calculation. The reason it tends to be rounded to about 3.14 is that in real terms, the accuracy to 2 decimal places is usually accurate enough. So if you imagine you are an architect and you need to do some calculations that are involving circles, it's unlikely that you are going to need to measure something down to 10, 15 decimal places. 2 or 3 should suffice. And typically engineers will just use 3 or 3.1 or 3.14 as an approximation for pi because it will be accurate enough to do what they need to do with it.
Okay, sir, thank you.
No problem.
Next question, Tejasvi. More and more hands are coming, so we'll stick it to next two only. Tejasvi, yes.
Sir, which app you were using to show us the representation of mean and all algorithms?
Good question. That is a website called Polypad, and it's free to use. Polypad.
Polypad.
Thank you, sir.
Last question from Vihan. Yes.
Sir, my question is that if the trick that we do with the 11 multiply by any number, we can do that trick with any 3-digit number or not?
You can, but you just have to start learning all slightly a few additional cases for the rule. You can go to 3 digits, 4 digits, 5 digits, but what you'll find is you need to do something slightly different each time. And so you're learning more and more and more steps, and the tool becomes less and less useful compared to a normal algorithm.
Okay, thank you, sir.
Well, I would like to ask one question.
Sure.
When we deal with mathematical operations like addition, subtraction, and multiplication, then we start from right hand side and we move to left hand side. But when it comes to division, then the direction changes. We start from left hand side and then we move to right hand side. Can you give some example or what could be the visualization to accept this?
The trick with that is to do it the other way around and see what problems occur. So if you try and do the bus stop method, right to left, as opposed to left to right, you'll soon come up against a whole host of reasons why it's not working well and why it's it makes it more difficult than the other way around. I think it's probably easiest to think of it in terms of it being the inverse and therefore the opposite.
Fine. Fine. Well, thank you very much, Dr. Supal, for answering all questions from the curious minds here. We have students from 10 years of age to 20 years of age. Right. It is now my privilege to introduce you to our special guest, a stalwart in science education and a great teacher of physics, Professor P.K. Ahluwalia, who is the president of Indian Association of Physics Teacher, the organization which takes care of international Olympiad programs for the country. Professor Ahluwalia has been a guiding force in nurturing scientific inquiry among students and teachers. We are indeed honored to have him here on this occasion. I request Professor Ahluwalia to express his findings and opportunities for educators from this session.
Yeah, thank you very much, Govindaji. And I think it has been a great exposure to me also. I must admit that because when I was seeing the title of this lecture, I was really finding it very exciting. Yes, but why? I mean, sometimes we do something like cooking. In cooking, somebody gives me a recipe. Do this, do this, do this, and you will find that that will be done. But then if I start asking in between, but why I should do it? Why this, and why this? I think the whole scenario changes and it becomes a very creative exercise. And that is what happened, Dr. Southall, in your lecture. It was just mesmerizing, I must say that. And I would love to buy that book myself also. Uh, and I would like to share it with my friends and students. I remember, when we do physics, or maybe sometimes we come across such problems. Suppose I have one, and if I add half to it, and then if I add half of half to it, and then I add half of one fourth to it, and if I keep on doing it, is it going to be an infinity or it will be a finite number? And the way you expressed this today, visualizing the things, and I think suddenly we find that I can make it uh, appreciate by a student of class standard, I mean, say fair five, that look, this answer is going to be equal to two only. And that comes from geometry only. I just need to make a, a simple scare, and I will keep on, adding another scare to it, adding half, and then keep on doing that, and I will find that the answer is two itself. I was reminded of this problem when you were doing those exercises. There was another thing. I had a wonderful teacher when he was teaching me division. He said division means subtraction. I said, how come it is subtraction? And he showed me that trick that look, if you want to divide 11 by 3, let me do one thing. Let me subtract 3. Write down 1. What do you get? 8. Again subtract 3. Now change that 1 to 2. And keep on doing it. You will know the answer as well as the remainder for that. I think sometimes we don't see things in this fashion. We just do things as if it's a kind of a step-wise exercise which we need to do. And the way you converted those algorithms into visualization was just fascinating. And I think hats off to you, the kind of research you have done on these things. It's just exciting. I wish if we can organize this program, not only for students, but for the teachers who should come here on this platform, interact with you, see that how things can be shown. The way you explained mean, median, and mode was very interesting. I remember there are some problems known as Feynman problems. And those are, he was very good at estimations. You also talked about estimations in your lecture. And he used to say, look, I don't want arithmetic mean when I have to do estimation. I would like to do geometric mean. And then somebody asked, why geometric mean? Why not arithmetic mean? And then one suddenly finds that arithmetic mean is biased when the things are heavy or say very, what you call light. Then it will get a biased answer to you. But when you do the geometric mean, that bias you will find it just goes away. I think these are a kind of exposures which are needed by our young minds if we are truly interested in making them creative learners. Uh, and once again, I would say that uh, there are some interesting people who started visualizing mathematics. You showed us a very interesting diagram of, I don't know how to say that because it was a very long name, which one has to remember, of 40 sides or 42 sides, something like that. And that is all fractals, isn't it? And those are very fascinating subjects on which we need to really talk about. So I think it was amazing experience for me. Sometimes when we grow up, we feel that we don't need to learn anything more. Dr. Southall, let me tell you very frankly, I learned a lot in this lecture. And hats off to your research into these aspects. Thank you very much. And it was great. And hope you will keep on obliging us in future also. Thank you.
Thank you. That's very kind. Thank you.
Thank you, Alu Alia sir, for your presence and kind motivation for such kind of programs organized by Professor Rajendra Singh, Science Exploratory. Seema ma'am, anything else to add? Well, so
Yes, yes. Yeah, yeah. Yeah. The representation was really wonderful, but I was also wondering that if when it comes into fractions, then it becomes a bit difficult. But same time, the whole numbers can be definitely showed and visualized for the beginners. So there has to be certain means gradation as per gradation, but of course, after all, it is wonderful representation. The algorithms are really wonderful. One can understand addition, subtraction, then division, as you have shown. It was really wonderful. Very nice presentation. I liked it. Thank you very much for sharing these things with
No
us and
problem.
our children.
Thank you. And thank you for the invitation.
well, thank you everyone. Now, as we draw this evening to a close, let us take a moment to appreciate our speaker, Dr. E.D. Hall, for showing us that learning can be both powerful and joyous. And yes, one can visualize mathematics too. Thanks to our teachers for being living examples of patience, dedication, and inspiration. Our learners for bringing energy and curiosity into this field of knowledge, and finally, our organizing team for making today's event possible. In the spirit of Teachers' Day and the festival here in India, let us recommit ourselves to education, not just as a profession, but as a sacred journey of learning and sharing. With a wish to meet Dr. Suthal in person for much such discussions, I would like to declare that the session is now over. Good night. Shubharatri.
Good night. Shubhrat.